Okay, so it turns out I'm a dum-dum and I don't know how to read. So we're going to do 21 again. So if you're watching 24 and you're like, WTF, what is she talking about? Ignore it. Okay, so 21. We have the electric field at a distance of E 0.145 meters from the surface of a sphere. Not from the middle, from the surface. Emphasis on the surface. So that's out here, not inside. So out here, the electric field is 1750 newtons per coulomb. And the distance away from the surface, so that's from here to here, is 0.145 meters. Assuming the sphere's charge is uniformly distributed, what is the charge density inside it? All right, so this is going to be one of our handy-dandy Gauss's law problems. So what we know, we have this big old sphere over here, blah, 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 blah. It's got a bunch of charge scattered about uniformly throughout. Now, because this is a sphere, and I want to know the electric field, or we know the electric field at some radius. At this radius, it doesn't matter if we measure the field over here, or over here, or over here, as long as we're at the same radius. So in order to keep our electric field constant at some radius, we want to draw a Gaussian surface so that that field is constant everywhere along that surface. So for spherical objects, the most common sense thing is to use a sphere. It takes advantage of symmetry, and also it takes into account that the electric field is going to be constant everywhere along the surface, which is what we want. All right, so Gauss's law is our good old closed integral of E dot dA equals Q and closed over epsilon naught. All right, so this part of the equation looks super duper gross and nasty and yuck, and it just looks like a horrible hot mess that you don't want to deal with. But 99.9% of the time, this is going to simplify down to a whole bunch of easy stuff. So our electric field comes out radially from a spherical object, right? So with respect to this Gaussian surface that we've drawn here, our electric field is normal to that surface. Similarly, our dA vector, by definition, comes out normal from a surface that we're looking at. So if I was looking up here, my dA vector would come out normal to that surface. So at this exact same point, my dA vector comes out normal to that surface. So dA and E are parallel to each other. And when we have two vectors that are parallel to each other, their dot product is just the multiplication of their magnitudes. So E is parallel to dA, which means E dot dA is just equal to E times dA. Magnitudes, not vectors. Yay! So there we got rid of a bunch of vectors inside of integral, because integrating vectors is no fun at all. Let's not do it if we don't have to. So now we have our closed integral of EdA, and we specifically choose our Gaussian surface so that the electric field is constant everywhere along that surface. That is the point of Gauss's law, because we want to solve for electric fields most of the time. In this problem, we're solving for Q. But in order to solve this for E, we need to be able to pull it out of that integral. So the whole point of Gauss's law is to get this E outside. And we can only do that if E is constant everywhere along our surface. So if we do that, E constant. Blam. So E is constant, so we can pull our E out and get the closed integral of dA. The closed integral over a surface is just finding the surface area. That's all it is. So don't freak out if you've never seen a little circle on an integral sign before. It just means go over the whole thing instead of just point A to point B. So this is going to be E times A. This area is always, 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 always the area of your Gaussian surface. So we're going to say area of Gaussian surface. Always. Always. All right? So in this case, it's a sphere. So our A is going to be the surface area of a sphere, so 4 pi r squared. So now we have E times 4 pi r squared is equal to Q enclosed over epsilon naught. That looks way better. That's just algebra. We all know how to do algebra. We're good, right? So now this question is asking us to find the charge density of this sphere. Our charge density is hiding inside of our Q enclosed. So just like with mass density, in order to get a charge density, you take the density times the volume. Exact same concept as mass density, just charge instead of mass. So because we're uniformly distributed, we can just say density times volume at the end. If we have a non-uniform distribution, it's not this simple, but we'll get to that when we get to it. All right, so in this case, Q enclosed is how much charge is enclosed within our Gaussian surface. So because our Gaussian surface is out here, our Q enclosed is going to be the entire sphere. The whole thing is in there. So our volume here is going to be 4/3 pi r cubed. Now this is the r of the sphere of charge, not to be confused with the r of my Gaussian surface. All right? So here my 4 pi's cancel out. So I have E times little r squared is equal to rho big R cubed over 3 epsilon 0. So solving for rho, we get 3 epsilon 0 E times little r squared over big R cubed. And that's it. So we can plug in numbers, but I trust you guys know how to multiply because I don't have my calculator with me right now, so whoops. Important thing to note, the problem tells you that it's 0.145 meters from the surface. So the radius of our Gaussian surface is 0.145 plus 0.355. So that's going to be 0.5 all the way over. All right. Okay, so part B wants us to find the electric field inside the sphere. So now we have our big, beautiful charged sphere. Charge, 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 uniformly distributed through that. We have our big R of the sphere. And now we want to find the electric field in here at some smaller radius. So I'm going to call that little r again. So everything that we did up here is going to be exactly the same, except for our Q enclosed. So I'm going to skip those steps so you guys can go back and try them again on your own. So our Q enclosed is density times the volume, right? But now the volume of the enclosed charge is only this chunk. So it's the charge that's inside of our Gaussian surface. So that's going to be rho 4/3 pi little r cubed. Okay? So that's the difference between finding it inside and outside. Your charge density is going to give you a different radius. So our electric field times our area is equal to Q enclosed, so rho 4 pi big R cubed, little r cubed over 3 epsilon naught. So I like finding the electric field inside because then all my little r's cancel out. So my electric field is the density times little r over 3 epsilon 0. Ta-da! So if we plot the electric field as a function of radius, our electric field increases linearly with r while we're inside our charged sphere, and then it decays like 1 over r squared outside. So you might be asked to do this at some point in your future. Not sure. But yeah, the end.